In today's video, we will begin analyzing the structure of vector spaces, and we start by looking at a subspace. We will define what we mean by a subspace. We will then look at a simple way of determining whether a given set is indeed a subspace, and then we will look at a few examples of subspaces. Simply put, a subspace is a subset of a vector space that is itself a vector space. Right, so a formal definition, let V be a vector space with the given operations of vector addition and scalar multiplication, and W be a non-empty subset of V. If W is a vector space with respect to the operations in V, then W is called a subspace of V. Now, unlike with a vector space, we don't actually have to go ahead and prove all 10 axioms to prove that a subset is a subspace. It's much simpler than that. This is explained in our theorem, which says, let V be a vector space with operations of vector addition and scalar multiplication, and let W be a non-empty subset of V. Then W is a subspace of V if and only if the following two conditions hold. If U and V are any vectors in W, then U plus V is in W. If C is any real number in U, or C is any real number and U is any vector in W, then C times U is in W. In other words, there's three things we have to show. First, that W is a non-empty subset of V. Okay, this is easily done, right? Showing it's a subset, that's usually pretty obvious. To show it's not empty, all we have to do is show that it contains the additive identity. Then, just show it's closed under addition and closed under scalar multiplication. All right, and we will go ahead and prove this. If W is a subspace of V, then it is a vector space. It must be. Therefore, 1 and 2 automatically hold, right? They have to be satisfied because it's a vector space. 1 and 2 are two of the properties. So now we have to prove the other direction. So conversely, let's suppose that 1 and 2 hold. We want to show that W is a subspace of V. Now, first, from property 2, we have that minus 1U is in W. Right, for all U and W. Now from 1, we have that U plus minus 1U is in W, which implies that our additive identity is in W. Then what we have is u plus the additive identity, which equals u for all u and w. And finally, the remaining axioms will automatically hold. Right? They have to hold because V is a vector space, right? Because they hold in V, which W is a subset of. Therefore, W is a subspace of V. Right, now we're going to say we have two sets W with two given vector spaces. We want to determine whether each is a subspace. So first we're looking at the vector space of R2. Right? And W is the set X to X such that X is a real number. Right? So first, clearly W is a subset of V. Right? It is a 2 vector. And clearly it is non-empty. Right? The additive identity is in W. This is easy to show by just saying, well, let X be 0. Now we have to show it's closed under addition and multiplication. So first let's take X, 2X, and add it to Y, 2Y. Well, we'll get X plus Y, 2X plus 2Y. Now that second component can have a 2 factored out. If we let X plus Y be W, we get W, 2W, and this clearly satisfies the condition to be in W because W is simply the sum of real numbers. So it is itself a real number. So it's closed under addition. To check under scalar multiplication, take C times X 2X. This will be Cx, then C 2X. That'll be Cx 2 times Cx. Replacing Cx with W, we get W, 2W. That also satisfies the condition to be in W, right? Because W, which is a real number times a real number, is itself a real number. Therefore, let's call this W sub 1. This is a subspace of R2. The second one, we're considering the vector space R3 and the set of all vectors x1, x2, x1 times x2, such that x1 and x2 are real numbers. We need to determine if this is a subspace or not. Okay, well, consider 1, 0, 0 and 0, 1, 0. Both of these are clearly in W, right? I said x1 is 1, x2 is 0, 1 times 0 is 0. Then I decided that x1 was 0, x2 was 1, and then we have 0 times 1 is also 0. Now what happens if we add them? we'll get 1, 1, 0. Well, 1 times 1 is not 0, it's 1. So this is not in W. So it is not closed under addition. So there's no way, let's call this W sub 2, is a subspace. So it is not a subspace of R3. Right, so when you look at problems like this, you have to first decide, is it a subspace or not? If it is a subspace, you have to show that the three conditions are satisfied, right? It's a non-empty subset, closed under addition, closed under multiplication. If you think it's not a subspace, as in case 2, then you must provide a counterexample. Right? So you would have to show that it's not a subset, or it's empty. Or you have to provide two vectors that are in W, but their sum isn't. Or you have to provide a vector in W and a real number such that their product is not in W. Finally, we're going to look at a special subspace called the null space. So given an M by N matrix A, we're going to prove that the solution set for the homogeneous system AX equals 0 is a subspace of Rn. And this is called the null space. So let W be the solution set of AX equal to 0 for some arbitrary M by N matrix A. Right now, clearly W is a subset of Rn, and the 0 vector must be in W, right? Because a homogeneous system always have trivial solution. We now have to show it is closed under addition and multiplication. Let A and B be two vectors in W. This means that A times A is equal to 0 and A times B is equal to 0, right? Let's look at A times A plus B. Well, this would be A times A plus A times B, right? That's a property of matrices. But we just said that is 0 plus 0, which equals 0. This means that A plus B is a solution. Right? So A plus B is in W. Now let K be a real number and A be in W. This implies, of course, that A times A is equal to 0. We now want to look at A times KA. Again, by properties, this will be K times AA. Well, that's K times 0, which, again, by properties of matrices, gives us 0, which means that KA is a solution, so KA is in W. Therefore, we conclude that W is a subspace of Rn. That concludes today's video on subspaces. In the next video of this series, we will continue looking at properties of vector spaces by looking at what's known as vectors being linearly independent or dependent, as well as what it means for a set to be a spanning set. As always, thank you for watching this video. I hope you learned something. and I will see you all in the next one.